In this section, we're solving trigonometric equations, and we've done things similar to this before. We've found angles that have particular trig values, but there was always some sort of condition attached to it. We would say find an angle theta where this was true and something else was true. Or we did an inverse function that had a specific definition. Now what we want to actually do is find all the solutions, every single possible solution there could be to this equation without any other restrictions. Okay? Um, but we start out the way that we have before with these kinds of things. We think about the unit circle. We think pi over what would work here. So we want the x coordinate on the unit circle to be 1/2. It's always over 3 over 4 over 6. This one would be over 3. Okay. And then we think about quadrant. Okay. This isn't the only angle that has a cosine of 1/2. Think about quadrants. Think about ASTC. Cosine's positive in the first and the fourth quadrants. And so we've already got our first quadrant angle. So we want a fourth quadrant pi over 3 angle. We also want some sort of pi over 3 angle that's in the fourth quadrant. Again, if you need a minute to figure that out, if you need to count around the unit circle or draw it, and use the reference angle, and do a little bit of math, addition and subtraction. If you have to figure that out for a little bit, that's okay. But the more you do this, the more you'll just kind of know that the pi over 3 angle in the fourth quadrant is 5 pi over 3. Okay? But those aren't the only angles that work here. Okay? So one angle that lands in the first quadrant with a pi over 3 reference angle is just pi over 3. But if we look at the terminal side of pi over 3 right here, if we look at where that angle would end up, there's multiple ways that you could rotate to land in that spot. Right? Remember the idea of coterminal angles. I could rotate an extra full circle and then land in that same spot. And if I land in the same spot, then I have the same trig values. So coterminal angles are also going to work here. Any coterminal angles of these. So I could add 2 pi, and add a full circle. If I add 2 pi, that would be 6 pi over 3, and that means we get 7 pi over 3. Would be another one. I could add 2 pi again, add 6 pi over 3. Again, common denominators, 2 pi is the same thing as 6 pi over 3. I could get 13 pi over 3. And I could keep doing that forever, right? So these equations, actually, how many answers are these equations going to have? If we actually want all solutions, there's actually going to be infinite solutions. It actually goes on forever. We're going to have a way to write out what the general solution looks like. We'll talk about in a second. But that's an important thing to realize. Anytime you're solving a trigonometric equation, as long as it has any solutions, it could be possible to have no solution. But if it has any solutions, it's going to have infinite solutions because you can always keep adding full circles. You can always find more coterminal angles. Okay? And of course, in addition to adding 2 pi, you could also subtract 2 pi. If I subtract 2 pi, subtract 6 pi over 3. Down here, I could have negative pi over 3. I could keep doing that. I could say negative 7 pi over 3, go on forever. I could add or subtract 2 pi to both of these sets of angles, and I could just keep going, getting an infinite number of angles. Okay. Well, here's how we represent that. I've got this note at the bottom of my notes here. Okay. So again, all trig equations are going to have infinite solutions. Again, unless there's no solution, because any angle you can find its coterminal angles, infinite number of coterminal angles. And so what we do is we say, well, the way we get those coterminal angles is we keep adding 2 pi. So to find any solution, we could add some multiple of 2 pi. Maybe we went in a full circle 3 times, so we would add 2 pi times 3. Or maybe we subtracted 2 full circles, then n would be -2. We would add 2 pi times -2. That would be like subtracting 2 full circles. So if we say 2 pi n, if we put plus 2 pi n, that's going to represent all the infinite solutions. And so we just have to note n would have to be an integer there. If you're trying to add a full circle, you don't want n to be a half, right? If n is a half, then you'd only be adding pi. That would only be half a circle. But we'll just kind of assume that's true. In this class, whenever we say plus 2 pi n, it's just going to be understood that we're talking about n being integers. 1 or -1, 2 or -2, 3 or -3, 0, whole numbers and negatives. Okay. So the way that we write all the solutions, the way that we write the general solution, is we say pi over 3 plus 2 pi n. So when n is 1, that gives us 7 pi over 3. When n is 2, it gives us 13 pi over 3. When n is 3, gives us the next one, n is 4, and so on. All those possibilities of adding full circles. And again, we could have n is -1, going backwards. And then the same thing for 5 pi over 3, we say plus 2 pi n. That's what we call the general solution. It's a way of writing out all the solutions when there's infinite solutions. All right, now notice though, when we do this, when we're solving this equation, we can have infinite solutions, but don't forget your inverse functions. What if I say inverse cosine of a half? If I'm using that inverse function, then for this input, there can only be how many outputs? Only one output, right? So just make sure you remember for the inverse function, you wouldn't have all these infinite solutions. You wouldn't even have these two. You would only have the one solution. All right, so make sure you keep that straight when we could have all these possibilities versus when there was some restrictions and we would only give one answer for a function. All right. So how about this one? If we want tangent of x to equal -1, okay, well, first of all, think about just tangent being 1. If tangent is 1, we're trying to figure out when does y over x equal 1, would mean that y equals x. And so what on the unit circle made the x and the y coordinates be the same? And that was your pi over 4s, right? So we're looking for some sort of pi over 4 angle here. We know pi over 4 is the reference angle. And then let's think about ASTC. If we want tangent to be negative, that's either the second or the fourth quadrants. So again, if you need a minute, you can always pause the video, figure out what's an angle with pi over 4 reference angle. It's in the second quadrant. What's an angle where pi over 4 is the reference angle in the fourth quadrant. That's going to be 3 pi over 4, and it's going to be 7 pi over 4. Okay, but those are only two angles, right? We want the infinite numbers of solutions. So what we want, I shouldn't put my comma there yet, we want 3 pi over 4 plus 2 pi n. We want 7 pi over 4 plus 2 pi n. Those are all of our solutions right there with those infinite number of full circles. Okay. Now that's a perfectly good answer. That's a great answer that will always get you full credit. You might not see that answer if you're checking like in the back of the book or something like that. What often happens is, again, we mathematicians are very lazy / efficient, notoriously lazy / efficient. And so what we do is we actually find a quicker way or a more efficient way to write out these solutions. So take a look at what these angles that we found look like. All of them are right here and right here. Right? One of the angles just went directly there. Some of them went in some full circles to get there, but they all landed in these spots. Okay, and so the way that we wrote our solutions originally was saying that, okay, I'm going to take a look at this angle, and to find the other ones, I'm going to go in a full circle, maybe go in a full circle backwards. But I'm going to do full circles to get all of these angles, and then separately, I'm going to look here. And I'm going to say to get angles here, I can start here and then go in multiples of full circles and find all those angles. Okay. Well, take a look at this. Is there a more efficient way to do that? Instead of looking at all these angles and all these angles separately, what if you started at this angle and wanted to get to that angle? Well, you wouldn't be going in a full circle anymore. Now you'd be going in a half circle. So you would just add pi, and that would get you from one of these angles to one of those angles. Well, then if you're at this angle here to get back to one of these angles, that's another half circle. So you could add pi, and it would get you back to here. Okay, so now instead of doing them separately with adding full circles and adding full circles, you can add half circles, and that will get you each of the angles in each of these spots that you need. So a more lazy slash efficient way of writing this that you might often see is 3 pi over 4 plus pi n. Okay. So the safest thing is just to list these out and put plus 2 pi n on each of them. If this kind of confused you, don't worry about it too much. Just to point that out, because you might see some of these things when you're checking your answers in the book. Okay? But you don't have to do the lazy slash efficient method. You can just do this, okay? Because you can't always just combine them. Take a look at what we had back here. We had pi over 3 and 5 pi over 3. They're not symmetrical. They're not evenly spaced. If you add a half circle here, it doesn't get you another answer. You'd have to go more than half a circle to get to this one, and then less than half a circle here. They wouldn't be evenly spaced. Okay. The only thing you might see in terms of being lazy slash efficient, sometimes they say, well, hey, 5 pi over 3, what if we look at that as negative pi over 3 instead? Replace pi over 3 as negative pi over 3 right here. Then we got pi over 3, negative pi over 3. We could call this plus or minus pi over 3 plus 2 pi n. Again, just trying to be efficient, just trying to use less ink, right? So you might see something like that when you're checking your answers in the book. The safest thing for us is just write what's in the blue here, but when you check those answers in the book, you might see some of this stuff in red there. Okay. All right, now let's take a look at this one. So now we're going to start to have a little bit of algebra to do before we can actually think about angles. All right, so this one, again, you can always think of a trig function as just one big variable. You could even do a u substitution if you needed. You could look at this as u squared equals 3/4. All right. And then, well, how would you solve that? You would have to square root both sides, right? Remember, this squared is on the outside. That's cosine of theta squared. It's just kind of a shorthand here. So I can go ahead and square root both sides here, and that will cancel out that square. Just make sure you remember when you add in a square root, what do you have to add? When you square root both sides, you have to put plus or minus. Make sure you don't forget that. If you forget that, you're only going to get half the answers. All right, so we've got cosine theta is plus or minus square root of 3 over 2. All right, and so we've got to think about our reference angle. So on the unit circle, we want the x-coordinate to be root 3 over 2. That's pi over 6. And then, well, if we thought about quadrants here, we've got plus or minus, right? So, well, I mean, I can circle all 4 of them then. Cosine can be positive or negative. That's all 4 of the quadrants. So I want all of the pi over 6 angles. And of course, I have to tack on plus 2 pi n to each of them, right? Again, if you need a minute to figure out what the other pi over 6 angles are, that's okay. But second quadrant is 5 pi over 6. And third quadrant is 7 pi over 6. And fourth quadrant is 11 pi over 6. All right. So we can just write out all 4 of those angles from each of the quadrants, tack plus 2 pi n on them, and call it good. That's a great answer. Right? It might not be the answer you see in the back of the book, though. They might be lazy slash efficient. So if we take a look at what we've got here, so pi over 6, it's going to look something like that. Pi over 6, 180 over 6, 30 degrees. And so all these have the 30-degree reference angle. They're 30 degrees away from the x-axis. Okay? And so if I look at this, I mean, the spacing from first quadrant to second quadrant is different from second quadrant to third quadrant. But what I could do is I could combine the first and the third quadrant angles. I could, those are a half circle away from each other in each direction. And then I could do the same thing with the second and the fourth quadrant angles. If you look at the second and fourth quadrant there, those are each half a circle away from each other. And so another option that you might see when you're checking your answers in the book, you might see pi over 6 plus pi n and 5 pi over 6 plus pi n. And that would also include all the angles that we need, because this one right here would include the 7 pi over 6, and this one right here would include the 11 pi over 6. Right? You could also see an ultimate lazy slash efficiency here, plus or minus pi over 6 plus pi n might be another thing that you see there, because that negative pi over 6 would be this one, and then adding the pi would get you to the 5 pi over 6. So any of those answers are fine. Again, most of us are just going to probably do what's in the blue here. I just want you to be aware of the lazy slash efficient red options there. Okay. Why don't you go ahead and give this fourth problem a try here. Go ahead and try solving number 4. Find all the solutions for me. Find the general solution. All right, so we've got several options here for what the general solution would look like. The most straightforward one, the safest one, is what's in blue there. We had a plus or minus, and so we just write all the ones from all 4 quadrants, tack plus 2 pi n on them, call them good. That's great. That's full credit. That's a great answer. Right? If any of you were feeling lazy slash efficient, then any of those red options would have worked as well. Right? So just to back up here, when we solved this, we had to add the 4 and divide the 2. And then we had to square both sides to cancel out the squared. Make sure whenever you square both sides, if you add the square root, you add the plus or minus. And then anytime we have something like cosecant, cotangent, secant, we always want to flip that around. And so that turned into sine of theta is plus or minus 1 over root 2. Some of you guys might have recognized it there. 1 over root 2, some of you guys have that memorized. If you didn't have that one memorized, then you do need to know that that's equivalent to root 2 over 2. Root 2 over 2 is the rationalized version of that. Again, you could always rationalize. You could say times root 2 over root 2 right there, and then you would get your normal root 2 over 2 that you're used to. Okay, and then this one, there's so many options because all of these are symmetrically spaced, and so you could just combine a couple pairs of them, or you could actually combine all 4 of them. You could say they're all 90 degrees apart. They're all pi over 2 apart. They're perfectly and symmetrically evenly spaced. All right, but any of those options is fine. As long as you got one of them, you should be good to go. All right, so now let's do a little bit more algebra. Right? So take a look at this first problem here. Notice the directions are a little bit different here. Now, instead of all the solutions, we're just going to limit ourselves, give ourselves a little bit less writing to do. But the other thing is now there's going to be a little bit more to do in the algebra before we can actually start figuring out angles. All right, so if we look at this first problem here, the first thought that a lot of people have is divide both sides by sine theta. There's sine theta on each side, so if we divide both sides, that would cancel those out, right? Well, we don't want to do that. Don't do that. Don't divide both sides by sine theta. Here's why. All right, you're not allowed to divide by 0, right? 5 divided by 0 is undefined. 0 on the bottom of a fraction is undefined. You're not allowed to divide by 0. Well, sine of theta equals 0 sometimes, right? There's a place on the unit circle where the y-coordinate is 0, where the sine can be 0. So if something can be 0, you shouldn't divide by it, because then maybe you're doing something that you're not allowed to do. Right? Instead, what you want to do is make the equation equal to 0 and factor it. So take a look at a simpler example that doesn't have trig functions in it. If you have x squared equals x, well, if you divided both sides by x, you would be left with just x equals 1. You would only get that one solution. But that's not all the solutions. You'd be missing a solution if you did that. Instead, what you'd want to do is subtract the x over and factor it. And then you would see that there's 2 solutions. So notice what would happen if we divide by x, we lose the solution where x can equal 0, because you're not allowed to divide by 0. So if x could equal 0, that's going to kind of disappear, and we're not going to see it anymore because we couldn't divide by something that was 0. So never divide by things that can equal 0 is the moral of the story here. Okay, so in this one in particular, don't divide by sine of theta because sine can equal 0. Right? Never divide by things that can equal 0. If you do, you're going to lose a lot of solutions to these equations. Right? Instead, the name of the game, what we're going to do a whole lot, is equal to 0 and factor. This is actually one of our most powerful equation solving tools that we have, other than the graphing calculator, of course, right? Without a calculator, we're going to put things equal to 0 and factor. Very powerful, because then we have that 0 product property. So I'm going to subtract the sine of theta over to the other side, and then I'm going to factor out that sine of theta. Instead of dividing it to both sides, I'm going to factor it out. Okay, and this is why it has to be equal to 0 in factor, because when it's equal to 0, I have that 0 product property, right? If two things are multiplied and equal 0, then you know one of them equals 0. That's only true for 0, right? If this was 5, then I couldn't say equals 5 equals 5. There's no 5 product property. If you multiply to 5, you could be 5 and 1. You could be -5 and -1, in which case neither of them would equal 5. It's got to be equal 0. It's only when two things multiply to 0 we know one of them equals 0. All right, so make it equal to 0 and then factor. You'll hear me say that a lot. Equal to 0 and factor. Okay, so now we can find our angles. Now we basically just got two separate problems. We can ignore this one and solve this branch. And so sine theta equals 0. Well, that's going to be quadrantal, right? That's not one of our pi over 3, pi over 4, pi over 6. We've got to think about on the unit circle, if the y coordinate is 0, well, y is up and down, so we didn't go anywhere up or down, so we're on the x-axis. So we're looking for either straight right or straight left. And so straight to the right, well, that could be either 0 or 2 pi, right? Well, notice the directions here. We just want these angles that are in the interval 0 to 2 pi. And notice there's a bracket on 0 and a parenthesis on 2 pi. So 0 is included. I can equal 0. 2 pi is not included. I cannot equal 2 pi. So I'm going to call this right side 0. And I'm not going to stick plus 2 pi n at the end of it, because I've restricted this here. I've restricted us. There's a limit to the kind of angles we can have. These are angles that are less than a full circle, right? And they have to be positive. If I add 2 pi n onto this, I'm going to get things outside of this. I'm going to get angles that are too big. So when you see this restriction, we don't want the plus 2 pi n. So I'm just going to say 0, and then over on the left there, that's going to be pi. All right, so those are the solutions for this branch on the left, and then we look at this one. So we will add the 1, divide by the 2, and get that secant is a half. I don't know a lot about secant. I know a lot more about cosine. So if secant is a half, cosine would be 2 over 1. Well, let's think about this. On the unit circle, we want the cosine to be 2. We want the x to be 2. Well, remember the unit circle, it was unit circle because the radius was 1. The distance to the edge of the circle was 1. So how could you go a distance of 2? You couldn't. Or think about the graph. Remember the graph? The graph of cosine bounced back and forth between -1 and 1. It was bounded, it was constrained, it was limited to y values only between -1 and 1. So how could you have cosine equaling 2? You couldn't. There's no place on the graph. There's no input value for cosine. There's no angles where cosine is ever going to be 2. Right? This is impossible, because cosine is less than or equal to 1 always. Cosine bounces between -1 and 1 and all the numbers in between. Right? So if this was the whole problem, then the answer would be no solution. But it's not the whole problem. We just don't get any answers from that half. We only have the answers from this half over here. Right? All right, so then we'll take a look at this one. So it's already equal to 0 for us, so we'll factor. We've got a nice GCF there, so let's factor out the GCF. And again, if you really need to on these, you can look at this like, this one was 2u times v equals v. You could look at this one like u to the fourth minus 4u squared equals 0. If you're really struggling, you can try doing something like that. Replace the trig functions with u or some other letter. But the functions are just like one big variable. So I can factor out the u squared here. I can factor out the cosecant squared. I've got it equal to 0 and factored. I can use that zero product property. And then I've got two separate problems to solve. Right? So here I need to square root both sides, which normally would mean I'd put plus or minus, but plus or minus 0, same thing as 0. So I don't need to worry about it too much there. Don't know much about cosecant. I know a lot more about sine. So if cosecant is 0, sine would be 1 over 0. Well, 1 over 0, though, that's undefined. Well, let's try to think about when sine was undefined. Think about the graph of sine. Where did it have any holes or asymptotes? It didn't, right? It never did. Sine is the y-coordinate on the unit circle. The circle doesn't have any undefined y-coordinates, okay? Sine and cosine are never undefined. The only one that would be tangent, or cotangent, or cosecant or secant, some of the reciprocal ones. But out of sine, cosine, and tangent, tangent's the only one that could be undefined. Sine would never be undefined. Let's look at this one over here. Cosecant squared x equals 4. Square root both sides. Remember, if I add a square root, I add a plus or minus. So cosecant x is plus or minus 2. Switch that to sine. We want sine to be plus or minus a half. So first I think about the reference angle, the pi over what? Pi over 3, pi over 4, pi over 6. This one would be pi over 6 on the unit circle, y being a half. That's pi over 6's. And then plus or minus means I could have all 4 quadrants. I can have first quadrant, second quadrant, third quadrant, fourth quadrant. So this can be pi over 6, 5 pi over 6, 7 pi over 6, and 11 pi over 6. And notice I'm not adding what to these angles? I'm not adding 2 pi n. The reason I don't add 2 pi n is because of this restriction here. All right? If this just said find the solutions to the equation, then I have to add plus 2 pi n. If I want all the solutions, if I want the general solution, then I got to have all those coterminal angles, all those infinite solutions. But because of this restriction, these are the only angles inside that interval. If I add 2 pi, if I get 13 pi over 6, it's going to be too big. If I subtract pi, get negative, or if I subtract 2 pi, get negative pi over 6, it's going to be too small. It's going to be outside that interval. Okay, so one last one here. So this one, I've got sine squared there, cosine there. I mean, I can try to make it equal to 0, see if we can factor it, but it's going to be a little bit trickier here. I've got sine and cosine. This one right now isn't going to factor, right? Well, here's where we're going to go ahead and use our identities. Notice up to this point, we haven't really done that too much. Like the rule of replacing things with sines and cosines. I didn't want to like replace cosecant with 1 over sine there. Would have made it much uglier. I didn't want to replace secant with 1 over cosine. Most of these we're not going to use identities. If you can solve it without an identity, just go ahead and solve it without an identity. Try it first without any kind of the puzzle stuff that we did from the past couple days. But this one I can't right now, so we have to use the identity. Right? So remember how we rearranged these here, right? So we had sine squared plus cosine squared is 1. So you can see before what we did was we found that then that meant cosine squared was 1 minus sine squared. Now we want to do the opposite. Now we want to figure out what does sine squared equal. So if I took a look at this right here, if I subtract cosine squared over, then I can figure out that sine squared x is 1 minus cosine squared x if I subtract cosine squared from both sides. And so in this equation, I can replace sine squared with 1 minus cosine squared here. Okay, we're going to take this and we're going to substitute it into that equation right there. So I'm going to have 2 times 1 minus cosine squared x minus cosine x minus 1 is 0. So then 2 minus 2 cosine squared x minus cosine x minus 1 is 0. I've got just a couple like terms to combine there. So negative 2 cosine squared x minus cosine x plus 1 is 0. Personally, I don't like my squared term to be negative, so I would divide over by negative 1. Make that 2 cosine squared plus cosine x minus 1 to 0. I just personally think that makes it easier to factor. And if you want, you could factor that right now. If you want to factor that right now, well, to get 1, you need 1 and 1. It's still going to equal 0 over here. And then you would say to get 2 cosine squared, I need 2 cosine x and cosine x. And then to get a positive cosine x, I would want plus 2 cosine x and minus cosine x. So you could just factor it as is. Now, if you're not comfortable with that, you can go back to u substitution. You can say u equals cosine x. You've got 2u squared plus u minus 1. And that would be 2u and u, 1 and 1, plus 2 minus 1. All right, and so you could use the u substitution to factor if you want, or just go ahead and factor it as is. That depends what you're comfortable with. So then here we would get cosine x equals a half. Here we'd have cosine x equals negative 1. On the unit circle, cosine being a half, that's pi over 3. We would need to think about ASTC. Cosine is positive first and fourth quadrants. Fourth quadrant, that's 5 pi over 3. Again, we don't put the plus 2 pi in because of that restriction. And then cosine being negative 1, we want the x-coordinate be negative 1. That's on the left side of the unit circle. And so that's pi. All right? No plus 2 pi n because we're just looking in the interval 0 to 2 pi. And so this one we do actually get solutions from both branches, and so we just have those 3 solutions all together.